Hey everyone and welcome to PrepFusion. So today we'll be starting the new chapter, that is the root locus, right? This will be a new chapter of control system. So this is a very important chapter, okay? And what do you mean by root locus, and what are like basic steps that you need to keep in mind, and also I will give you a basic intuition of why do certain rules are like that, right? Why do we follow certain rules? Okay, so I will give you a basic intuition. Obviously I won't give you a full proof, right? Because that is not important and that is not useful also, because in gate, right, what mainly we have to do, obviously we have to solve questions. But if you get a intuitive approach and intuitive idea of why does the rules occur like that, or why does the rules follow those conditions, then it will be much more easier for you to solve, right? So yeah, that we'll do. Okay, and this is basically the first lecture. So in this first lecture we'll first understand the definition of root locus, basically what is a root locus, and few rules of root locus for k greater than 0. Now what is this k? K is basically my system parameter. Then we'll do the questions on magnitude and angle condition for system parameter k. Here, right, k is the system parameter. We'll understand what is k slowly in the next few slides. So yeah, let's start with what is a root locus. So let's read this, right? Root locus is the locus of the closed loop poles as system parameter is varied. So I will come to system parameter. Okay, but what do you understand? It is a locus, right? We have studied, right, in class 11th or 12th that what is locus? Locus is basically trace or path, right? Locus is basically trace or path. So it is basically locus of closed loop poles of closed loop poles as a parameter is verified. Anything that is verified as any parameter is varied, right? Anything that will be varied will be with respect to my closed loop poles. So if I can plot my closed loop poles with respect to the change of those variations, that I will call as root locus. So what is root locus? Root locus I can also say as loci or trace of roots. Basically it is a trace of roots, right? Wherever are my roots in the sigma plus j omega axis with respect to certain parameter, that will be my root locus. So here I have a system, right? This is a system, okay, and this is the OLTF. What is the OLTF? OLTF is g of s into h of s. Okay, that I hope you remember, right? You didn't forget. So now let's take example of few system parameters. So here I have two systems, right? They are both different. Why? Because this k is outside and here this k is inside. Okay, so what is this k is known as the system parameter. Okay, this k is known as the system parameter. This is what will vary. Okay, for now what will vary, like in the first case, right, what we'll do, this k will be positive. Okay, later on once we get accustomed to this, my k will also be negative. That we'll see. For now this k is positive. Okay, so this k is also known as system parameter and this k is also known as system parameter. So they may be present in multiple forms, right? Inside this g of s also or outside this also. Okay? But what you have to do, first you have to do is find the OLTF. So what is the OLTF for this one? OLTF for this one is basically k upon s plus 1 into s plus 2, because my h of s is 1 only. So OLTF is this one, right? OLTF is this one. Okay, and what is the OLTF for this one? So this is the OLTF 1. Okay, this one has also the OLTF same, but what is the difference? The difference is my k, right? K is here. Okay, k is here only. So that is it, but the actual final equation they are same, right? So that is the main thing. So it may be on the outside, it may be on the inside, it doesn't matter. But what you have to do, you have to find the OLTF, and by OLTF you can find your characteristics equation. Okay, so by OLTF you can find your CLTF, right? How? For a unity feedback. Okay, even if it is not unity feedback, let's say this was unity feedback here, let's say there is some h of s here. So what is my CLTF? CLTF is g of s upon 1 plus g of s into h of s, right? G of s into h of s. Okay, This is my CLTF. I hope you understand, right? So what is my characteristics equation? My characteristics equation will basically give me the roots of the CLTF, right? I hope you understand it. You remember that this is the numerator and this is the denominator, and how we find the poles, right? Basically roots, you mean that by the poles. So I should write here trace of roots or trace of poles of CLTF. So mainly what I'm interested in, the poles of my CLTF. Why am I so interested in my poles of CLTF? We studied the time response chapter, right? Okay, just studied the time response, and the poles define the damping, okay, also stability and much more, right? My system parameters are defined mainly by pole, right? Okay, so that's why I'm very interested in knowing where does my pole lie with variation of certain system parameters, right? That's why. Okay, so it is the loci slash trace of CLTF poles, okay, or I should say poles of CLTF. Okay, poles of CLTF. So this is what basically this root locus is, right? So yeah, that's why I'm very interested in my poles of CLTF. Now if I make this one 1 plus g of s h of s equals to 0, so this will give me the roots, right? Roots. So this is the, what is this? This is the characteristics equation. So let me write this one as characteristic equation of CLTF. So now basically this will give me the, if I equate this with 0, what will this give? This will give me the closed loop poles of characteristics polynomial, that is basically roots of this equation, right? So this will give me the poles of CLTF. Okay, that we already know, just like writing it down for better understanding. So what I'm mainly interested through OLTF, right? This is the OLTF, right? GS into h of s. Through OLTF I have to find my CLTF. So in root loci, what we'll do basically through the OLTF, then we'll vary the system parameter k, and by varying the system parameter k, I will find my poles of my CLTF, the loci of poles of my CLTF. So this is the standard form of a OLTF. What is this written here? There is k. Now k is the system parameter. So let me write k is a system parameter basically, and you have to remember this is not the DC gain, right? This is not the DC gain, okay, not the DC gain. Just remember this. DC gain is different. DC gain is different. This is not the DC gain. This is a system parameter. So you may ask, like, then what is this? So when we will study controllers, right? When we will study controllers, there we will see like there is something called as proportional controller, PI controller, all those things. So we vary the gain of the proportional controller to see how my system behaves and to change few characteristics of my system. So yeah, that is important, right? That is important. So that is basically what this k represents. So for now you will not understand this. When we will study the chapter controllers and compensators, there you will understand. Okay, so yeah, this was this one. So for now what you can say is this is the gain of the system. Gain of the system. Now what else is present over here? What else is present over here? What I can see is I have this z1 z2, like how many number of zeros I have? I have m number of zeros, right? M going from 1 to m, so I will have m number of zeros. And how many number of poles I have? I have n number of poles, right? So let me write this down. So I have m number of zeros, and what are these zeros called? These zeros are called open loop zeros, because these zeros are present in OLTF. Okay, these are not just zeros normally, because these are open loop zeros. These zeros I am not interested in. I am mainly interested in my closed loop poles, right? So but this will come in handy to find my closed loop poles, that we'll see. So this is known as my M, okay, and M is known as the open loop zeros. Okay, so these are the open loop zeros. So how many open loop zeros I have? I have like M, which are minus z1 minus z2 and goes on still minus zm, right? So these are my open loop zeros. Now what is my n equals to, what is my n? So n, I have n open loop poles, right? Now these are not just poles for CLTF, these are open loop poles. So I have n open loop poles. Okay, so now what are these poles? These are P1, P2 minus P3 and goes on until minus Pn. Okay, so yeah, these are basically about the poles and zeros. Now can you tell me, by seeing this equation or by seeing this equation, this is the characteristics equation of my CLTF, right? Can you tell me the order of my CLTF? What will be my order of my CLTF? Okay, closed loop transfer function for this one. So here, right, this is CLTF. What will the order? Order will be defined by the highest power of this polynomial, right? Highest power of this polynomial. Now tell me what is the highest power of this polynomial. So let me take this one. Okay, I will firstly copy this one. Okay, I will copy this one only. So let me pose you a question. You tell me what will be my order of CLTF. Okay, what will be my order of CLTF? So if I can see that, let me first take this equation. Okay, and you might answer that it is like I have m open loop zeros and poles, then it may be m plus n, right? Okay, m plus n. Then you are wrong. Why? Let me like write this equation, then also you will understand that what is happening here is like this is my g into h of s, right? This one, this is my g into h of s. So if I write this equation, let me write this equation. So this is 1 plus, let's say, k into s plus z1 into, it is going on until s plus zm, and this is s plus p1 and it is going on until s plus pm equals to 0. Okay, so if I do the cross multiplication, right, if I do the cross multiplication, what do I get? I get here s plus p1 into dot 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 s plus pm, and here I have k into s plus z1, and it is also going on until s plus zm. Okay, this is not, sorry, this is pn actually, sorry, this is not. Okay, so now what what do we know is that generally, right, generally for a realizable system and for my system to be like system transfer function to be proper, the number of poles will be always greater than the number of zeros. So, or like for the OLTF also to be proper, right, for the OLTF to be proper transfer function, my number of poles should be greater than number of zeros. Okay, and for my system to be realizable. Okay, else it may so happen, the question may come that number of zeros are greater than number of poles. It may so happen, but most of the cases my number of poles will be greater than number of zeros for my system to be realizable. Proper transfer function and system to be realizable. number of, like n should be greater than m. Okay, n should be greater than m. It can be equal, but n should be greater than m. Okay, so from this equation, can you tell me what is the, okay, I should write 0 over here also. So from this equation, can you tell me what is the power, highest power of s? If n is greater than m, so whatever here I have m terms, right? And at max I can get s to the power m in multiplication. Okay, and here how many terms I have n terms, right? N. So at max I can get s to the power n. So one side I'm getting s to the power n, another side I'm getting s to the power m. So which one has highest power? S to the power n. So what will be my order of my CLTF? So order of my CLTF will be n. So hence CLTF will be n. Okay, so order of my CLTF will be 1, n, right? So yeah, I hope that clears the point, but this is only valid for this one, right? This case, when this is true, then this will happen, but most of the time this is true because this is what we use in our system practically. Okay, so this was one case about the order. So if we know the order of CLTF, then what we know, that how many number of roots we will have? We'll have n roots, right? So we'll have n poles. Basically we'll have n poles of CLTF. Okay, and what does this n pole represent? We'll understand slowly. Okay, so now, right, like this is basically what is root locus is. Root locus is variation of closed loop poles with respect to open loop poles and the open loop zeros as a function of k. Okay, so we'll see like how does this happen. Okay, how does this happen? But this is what my root locus provides. My root locus provides a graphical visualization of all this. So root locus, once we do one example, you understand the graphical okay, so root locus provides a graphical representation of all this variation, right? So yeah, this is what this is. Now let's go for the case one. Okay, as I told you earlier as well, where my this system parameter is greater than or equal to 0. Okay, so obviously if system parameter is equal to 0, there is no significance as such. Why? Because you may see that if my k is 0, right, if my k is 0, my OLTF becomes 0. Okay, my OLTF becomes 0, then there is no control system or there is no system itself. So yeah, that is, we make it just tending to 0. There is some reason, we'll just see now. Okay, we'll just see now. So my system parameter is non-negative basically. System parameter is non-negative. Okay, so first there are two cases. So first we'll do, this is case 1. Okay, so what we'll do, we'll find the closed loop poles when my k is tending to 0. Okay, obviously it is not equal to 0. We'll choose two extreme points, right? Choose two extreme points and we'll see, we'll try to find out our closed loop poles. This is how we start a root locus. This is not the like start of how to plot the root locus, that will come later. Okay, this is just to give you basically the variation of like k with respect to my closed loop poles, right? Like how the k is varied and how my closed loop poles are formed with respect to variation in k. Okay, so if my k is tending to infinite 0, tending to 0, then what is happening to closed loop poles? So then closed loop poles, where will closed loop poles be? So we have to see right, but just keep this in mind, this has no actual significance, like k equals to 0 has no actual significance. So k equals to 0, why? Because the system will be gone. Okay, this is just for plotting the root locus. Okay, this is just for plotting the root locus. Okay, so yeah, now let's write my characteristics equation. So what is my characteristics equation? It is this one, right, which is 1 plus g of s. Now let's assume my g of s, I have only one pole and one zero. Okay, just taking one example. So we just want to see how my CLTF poles are for with respect to my OLTF poles and zeros. So let my g of s equals to ks plus alpha by s plus beta. This is what my system variation is. Okay, so like alpha is the zero of the OLTF and beta is the pole of the OLTF, right? Now if I put k equals to 0, okay, my characteristic equation is 1 plus g of s equals to 0. That is my characteristic equation, right? So if I put k equals to 0, what will happen? This will be 1 equals to 0. So that is not possible. Okay, that is not possible. So what I will do, let me see. Okay, so simply putting k equals to 0 won't work. So what I will do, I will just simply rationalize. So let me first write the characteristics equation. This is s plus a alpha divided by s plus beta okay equals to 0. So simply putting here k equals to 0 won't cut it, right? So what you have to do, we have to simply cross multiply this s plus beta here, then we will put k equals to 0. That will be much more interesting. So if I cross multiply s plus beta plus k into s plus alpha equals to 0, what do I get? So here now if I put k equals to 0, as k is tending to 0, okay, this one will also tend to 0, this one also will tend to 0, right? Because this is very small number. Okay, this is very small number, so this one also will tend to 0, but this one will still remain. So here, from here, what I can see is I can get the equation s plus beta equals to 0 or s equals to minus beta, which is basically open loop pole of the OLTF, right? Basically this is basically the open loop pole. So what can we infer from here? So what we can infer is, let me keep this one over, that my poles of CLTF will be equals to my poles of OLTF as my system parameter as k tends to 0. Okay, not equals to 0 but tends to 0. So this is very important. Okay, this is also one of the rules of my root locus. So this is very important. Let me bring this one down. Okay, so this was the A part, basically, as my k tends to 0. Now what will happen to my closed loop poles as my k tends to infinity? So let's see that also, right? So this is the part B, basically. If my k tends to infinity, what will happen to my closed loop poles? Okay, what will happen? So again, right, just remember one thing here, right? The number is same. So like my closed loop open loop poles I have n, right, and closed loop pole will also be n. Okay, but here there is one difference. My closed loop poles will be n, as I already explained, right, as I already explained. So I will write here n because here there is a slight difference, n closed loop poles. So what is the difference? Basically it may so happen my zeros are less, right, because my zeros may be less. Okay, my zeros may be less, so I should write this as like my zeros can be less, right, zeros can be less. So if zeros are less, then I will get something else, that also will understand. Okay, so okay, I should have taken like 2 poles and zeros, then that would have been easy, or like no poles at all. So yeah, that I will do later. But first for this one let's solve, then I will do the next one. So if k tends to infinity, again I will write my characteristics equation. So this is my characteristics equation, right? Okay, and this is my g of s basically. Okay, so like now I put this one here, what do I get? I get k s plus alpha s plus beta equals to 0. Okay, now k is tending to infinity, right? So if k tends to infinity, this one will blow up, right, go to infinity, and infinity equals 0. That is also not making sense. So when something tends to infinity, what we do? We divide, right? We divide and try to make it 0, right? Just remember limits, right? Limits chapter. So I will divide by k, so this will be 1 by k plus s plus alpha, and what I will do is like multiply the s plus beta over there, right, because I have to eliminate few things also. Multiply s plus beta over here. Okay, else like simply this one, like if I keep s plus beta over here, this one will go to 0, and this s plus alpha by s plus beta will be equals to 0, which means basically this one has to go to 0. That is all the same thing. Okay, so this is equals to 0. Now if my k tends to infinity, what will happen? If k tends to infinity, basically this one will go to 0, right? If k tends to infinity, this one will go to 0. So if this one goes to 0, so I am only remained with this one. So now my equation becomes s plus alpha equals to 0. So my s equals to minus alpha, basically. So if my s equals to minus alpha, what does this mean? What is alpha? Alpha is my open loop 0. Open loop 0, right? Alpha is my open loop 0. So if my k tends to infinity, then my root locus or the closed loop poles goes to open loop 0, right? Okay, hence what can we infer, okay, from here? CLDIV is zeros of, I should write here of also, this one I missed. So this is basically poles of OLTIF, right? And this is zeros of OLTIF. Okay, as k tends to infinity. So there is one catch over here. Now what if my number of zeros is 0? I mean, what if my number of zeros is less than number of poles, but still I will have n number of poles and number of zeros is still lesser, right? So they are not equating each other. Okay, then what will happen? Now what if my number of zeros is less than my number of poles. Then what will happen? So let's see, right? Let's take an example. Okay, so let's take an example where my OLT, right, GH of S into HH of S equals to K by S plus beta. I don't even have a zero this time, I only have a pole. Okay, I will have a pole. So if this is the case, then what will happen? Basically, right, what I can write, what is my characteristics equation? Characteristics equation is this one, 1 plus K by S plus beta equals to 0. And now what will I do? If I divide by K and multiply by S plus beta, what will happen? So dividing by K and multiplying by S plus beta in this whole equation, I get S plus beta by K plus 1 equals to 0, right? 0. So now, right, now if my K tends to infinity in this equation, if my K tends to infinity, what will happen? And my S is finite, if K tends to infinity and my S is finite, what will happen? This will go to 0. Now the what does the equation states? 1 equals to 0. Is that correct? Very famous equation, right? 1 is equals to 0. So is that correct? That is not possible, right? That is not possible. So this is the case that happens when I have poles more than number of zeros. Number of poles is more than number of zeros. So now I will, like, what will happen is basically this S, right, it will go towards infinity. Direction we can't tell, it will depend on the location of the poles and zeros of the OLTF, but what we can tell is this S will go towards infinity, right? This S will go towards infinity magnitude. So I will give you one intuition. Okay, let's see one intuition, and from there we'll understand. So this is sigma T plus let me write this as j omega t. Okay, j omega t, and this is, I'm just breaking down my S, right? So if this one is going to infinity, okay, this one has to also go to infinity, so that, like, in this case, what will happen? In this case, this one has to go to -1. Okay, this whole equation has to go to -1. So limit, if I want to do, right, so what I want to write here is that limit whatever the variables are, limit as S tending to, like, whatever, okay, and K tending to infinity of this equation, okay, by K by beta by K should give me -1. Why? If I get -1 over here, then this -1 and +1 will get cancelled and I will get 0. I'll get 0. So how to get -1? How to get -1? S is varying, right? How do I get -1? Think about it. If S goes to infinity, can it go to -1? No. If S goes to infinity, then we compare the coefficients, right? When it goes to infinity, this is 1 and this is also 1, it will be 1 only. But if S goes to -infinity, then this will be -1 divided by 1, which is -1. So if S goes to -infinity, then I can see, right, that this equation is satisfying. So this is a asymptote, basically. What is the magnitude of S going? The magnitude of S is going to infinity. So I will not derive this one, okay, this will waste time. Okay, I just gave you a basic intuition from here, and that will do. But, like, S will not always go to -infinity. It depends on how many zeros I have and how many poles I have, and all those things. Okay, it depends on many factors, but this is one of the factors, right? This is one of the factors. So from here we can understand. So what I can say is, one thing is for sure, that my magnitude of S has to tend to infinity. Direction I don't know. For characteristics equation to get satisfied. Okay, if my characteristics equation has to be satisfied, then this magnitude of s has to go to infinity. Okay, go to infinity. Now can I tell about the direction? Direction I don't know. Okay, so I will write can't tell about the direction. Okay, I can't tell about the direction. Okay, but one thing is for sure, my this will go to infinity. Now what does this mean? This is not actual 0, right? This is not actual 0. Okay, still I'm getting a 0. Still I'm getting like this is like a 0, right? Okay, because this is like a 0 of the OLTF, that we mean, right? As we will understand later on, that my root locus starts from poles of OLTF and terminates at zeros. Like in this case, right? A root locus as k equals 0, it starts from poles here, starts from poles, okay, as k equals 0 tending to 0, and as k tends to infinity, it ends at 0, right? Ends at 0. But here, right, my s is tending to infinity, so this is also 0, okay, but not a real 0, because we don't even have a 0 in the OLTF, right? Okay, we don't even have a 0, so this is known as the virtual 0. Virtual 0 basically. Okay, because this is not a real 0. Okay, that's why we call it a virtual 0, because like this 0 isn't present in my OLTF, right? That's why I will not go to further explanation, because this will just waste time. But let's write few formulae about the virtual 0. So if I have n closed loop poles, right? If I have n closed loop poles, then out of those n closed loop poles, as k tends to infinity, as k tends to infinity, what will happen? As k tends to infinity, I will have m open loop zeros, I will have m open loop zeros and n minus m virtual zeros, because the remaining, like I will have poles, right, of CLTF, right? I will have n poles of CLTF, so m will be done by those zeros only, m will be covered by those open loop zeros only, but I will still have to make n, like n minus m closed loop poles. Where will they come from? They will come from this virtual 0. So this is n minus m virtual zeros. Okay, let's apply this in this example only. So how many zeros I have? I have 0 zeros, right? And I have one pole. Okay, so as k tends to infinity, I will need one pole. Okay, I will need one pole, but I don't have any zeros. Where will that 0 come from? That will come from this virtual pole 0 basically. That is 1 minus 0, 1 virtual 0 I have. So just remember this. Obviously, like I told you conceptually also, but you have to remember this also, that number of virtual zeros equals to n minus m. Okay, so to remember this also, like this, what we can write in short form also, that like this is known as the, okay, let me take this. ZB I can write, this is number of virtual 0 is n minus m, or a few people what they prefer is like they want to write the number of poles as p and write the number of zeros as z. This is easier to remember, so you can write like this one also. This p is the open loop poles and the z is the open loop zeros. Okay, so yeah, these are the things, right? These are the things about the root locus. So what is happening to my root locus? My root locus starts at k equals 0. So root locus basically starts k equals to 0, right? Okay, and what does it end? It ends at k equals to infinity. So that's how we vary, right? We vary something from 0 to infinity. But obviously, what is the important thing is k is actually not equals to 0, but in root locus, obviously we have to start from somewhere, right? That's why we make it k equals 0. But in real life, if you make k 0, there is no system, right? And root locus ends at k equals to infinity, right? Okay, so now right now so basically where does it start from? It starts from my open loop poles, right? Open loop poles, already established that. So it will start from my OLTF poles, okay, and where it will end at my OLTF zeros and my virtual zeros, right? Virtual zeros, okay. This is how my root locus basic structure is. It's starting from my OLTF poles, as I saw here, right? As I tend k equals 0, so obviously you vary something, you vary from minimum to maxima, right? That's what you vary. So k is varying from minima 0 to maxima. So if I tend my k towards 0, what do I see? My closed loop poles tends towards my open loop poles. Okay, so my closed loop poles equals to my open loop poles when my system parameter k is going towards 0. Now if I tend my, like I'm going towards the end now, if I tend my k towards infinity, what is happening? My poles of CLTF will be equals to zeros of OLTF. Okay, my poles of CLTF will be equals to zeros of OLTF. So that is what my basic this one will be, like my flow will be, right? Flow will be from open loop poles to open loop zeros. Okay, but obviously as I explained, right, that my open loop zeros are not enough, right? If they are less than my open loop poles, then obviously I will have few virtual zeros. Or what is the other way of saying the flow? Okay, as we are plotting the root locus, and what is the root locus? It is basically the trace of my closed loop poles, right? So what I can say, it is going from my CLTF poles to CLTF poles itself, right? CLTF poles itself, because like it's just the, like at k equals 0 I have one CLTF poles, and here I have some other CLTF poles, right? So it is going from one pole to another pole. So it is, the whole plot is for poles only, not for zeros. Okay, just remember the root locus is a plot for the CLTF poles, okay, not the zeros. CLTF zeros has, like in root locus, CLTF zeros has nothing to do with, right? Nothing to do. Okay, so now what is the another thing? Another thing is that how many root locus, the number of branches for root locus, how many will I have? Okay, now what do I mean by branches? So let's say, what do you mean by branches? So branches, this will be also written, I think, at next step. So this is the next step that we're going. So branches is basically locus of each pole with variation of my parameter k. Okay, locus of each pole by variation of parameter k. Okay, so what does this mean? So I will have multiple poles, right? Let's say if I have, obviously the order of the OLTF is 2, right? Or order of the characteristic equation is 2. So if I vary my k, my two poles will vary, right? Simple as that. My two poles will vary. Now each of the variation of each of these poles, the trace of those poles or the locus of each of those poles is known as the, is known as what? Is known as the branches, number of branches. Each of the poles. So let's say I have pole here, pole here. So the variation of each of those poles are known as the number of branches basically. Okay, so yeah, that is basically it for branches. So tell me, how many branches will my root locus have? Okay, if I have number of zeros of OLTF is m and number of poles of OLTF is, sorry, m is the number of zeros of OLTF and n is the number of poles of OLTF. Tell me how many branches I will have. Okay, what was the definition of branches? This one, right? So locus of each pole by variation of parameters. So how many, so think how many poles will I have? How many poles will I have for CLTF? It will be n, right? N. So how many branches will I have? It will be also n. So the root locus will have n branches, right? The root locus will have n branches. So why, if order of characteristics equation is n, right? If order of characteristics equation is n, okay. Why? Because I will have n number of closed loop poles. This means I will have n number of closed loop poles. Okay, so yeah, this is basically about the branches. So we'll understand slowly. So next, these are the rules for sketching the root locus basically. So obviously I will not go into too much in depth. Okay, I'll just read this. Okay, and it's just this notes you will get and you just read this. Next lecture we'll do the example, and there obviously we'll go more in depth to these rules, right, and how to utilize these rules. Okay, these are the rules for sketching the root locus. So I have my characteristics equation, which is 1 plus this k into s plus z1, this standard form, right? So here we have written the root locus traces the evolution of the roots of this equation with variation k. We know, right? Obviously, like the variation of roots of my closed loop system with respect to variation in k, that I plot in root locus, right? Root locus. So like, what is the axis of root locus? Now it is the evolution of roots. What axis do we put roots in? Tell me. Do we put in imaginary and real, something like that? Yes, it was sigma plus j omega. So what are the roots? Roots are basically s, right? S is the roots, the solutions basically. Okay, so I will put my axis as sigma and j omega. That will be my basic axis for plotting my root locus. Basically it is a variation of closed loop poles, so it will be somewhere around sigma plus j omega, somewhere in this whole plane, sigma j omega plane, right? So yeah, that I hope you got in your head. Now root locus will have n branches slash curves. I hope you understood what does branches mean. Okay, I will not go further in deep. So like, I will just read this one out. Okay, just a bit. So firstly we have to locate the open loop zeros and poles in the complex plane. Why? As I told you, right, my root locus starts from open loop poles and open loop zeros. Okay, so those are important. The starting and ending point, easy to find it just by seeing the OLTF. So those I will mark first in the root locus, and then I will further proceed. Once we solve one example, they will understand. Next is locate the root loci that lie on the real axis. Okay, this one is difficult to understand. We'll not go into this. Okay, and next is we have to determine the asymptotes of the root loci. Okay, what does basically asymptotes mean? What does basically asymptote means? So asymptotes basically indicates the trace of my closed loop pole as my test point goes to infinity, or asymptotes indicate the trace of the virtual zeros, right? Virtual zeros basically. So what does asymptotes mean? So obviously we're not understanding the rule. I'm just telling you the meaning of asymptote. We'll understand obviously, as I told, right? We'll understand once we solve one example. So asymptote, what is asymptote? Asymptote basically indicates the trace of closed loop poles. as my test point, like whatever I test, like I will also explain what does test point mean just in a bit. As my test point tends to infinity, as my test point tends to infinity. So that is what my asymptote means basically. So like how do we do that, how like we solve it, that we understand like in example. Or this is, what does this mean? This means like how will my root locus look if my test point st tends to infinity. So how okay. So this is one important point about asymptotes. Now these are obviously like angle of asymptotes, points of intersection of asymptote. So these we will understand once we solve one question. These are the formulas. I will also give you a bit of intuition about how these formulas came up. Okay, so yeah, not going too much into details. Now like the next step is determine the breakaway and breaking points. Now what is breakaway and breaking points? Basically, okay, this one also you will not understand. Just go through this. Okay, if you understand, that's good. If you don't, like we'll solve, right? And this one is the like solution of how to find breakaway and breaking point. We'll do this. Okay, and like these are few like another, the angle of departure and angle of okay, sorry, angle of departure from open loop pole and angle of, okay, this is actually wrong. I'll correct it. Okay, angle of arrival and angle of departure. Okay, so what does like this complex zero, right? Always something will come to it, so it will be angle of arrival. Okay, angle of arrival. So don't worry if you don't understand. Okay, this like this two slides, this all these slides will understand in the next lecture. Okay, like when we solve a question, this I'm not going to too much detail. Okay, so all this we will understand. This I have just written this down, who know root locus from start, and like they want to again revise the steps, right, and the rules, so they can directly see from here. Okay, directly see from here. So a few key points I want to tell about root locus. These I will tell you a bit of, give you a bit of intuition, right? What is the intuition? That my root locus is always symmetrical about my real axis. Okay, why is this the case? So let me first draw one axis, right? So what will the axis? Axis will be sigma and j omega, right? So axis will be sigma and j omega. Okay, sigma and j omega. Okay, so axis is sigma and j omega. Then what is the case? Then basically, let's say my root locus has some pole over here, right? My CL has some pole over here for some value of k. Now can this pole lie alone here? This is possible. You know, right? If it is in the complex plane, then I will always have a conjugate, right? Always have a conjugate. That we have already established in time domain response also. So it will have to lie here, over here also. So what does this mean? What does this mean? Again, if I have a pole over here, okay, for any value of k, I will also have to have a pole over here also. So what do I see? It is symmetrical about my real axis. Okay, that's why this is mentioned. It is symmetrical about real axis. So why is this the case? Obviously we know already this, right? Okay, I will keep this. So why is this the case? The case is like this one, because as the coefficient of my characteristic equation are real, then I will always get my like roots as complex conjugate pair, right? As a pair. Okay, because my coefficients of my characteristic equation are real. Always get okay sorry always get complex conjugate. Okay, again pair of roots. Okay, complex conjugate pair of roots. So yeah, I hope you got the basic intuition why my root locus is always symmetrical about the real axis. Now what is the second point telling us? The second point is telling us the root locus will only exist if the total angle contributed by all open loop poles and zeros across the observation point is odd multiples of 180 degrees. Okay, uh, let's understand this, right? So what does this telling us is that all the open loop poles and zeros, the angle that they contribute to my observation point, basically the test point, will be odd multiple of 180 degrees. So this is also known as the angle condition. Okay, also known as the angle condition that we'll see that will prove, right? So what is my CLT basically? I hope you haven't forgotten yet. What is the CLTF? CLTF is basically C of S upon R of S, which is equals to G of S upon 1 plus G of S into H of S. Okay, so this is what my CLT is. So like, what is my characteristics equation? It is again, right, characteristics equation equal of CLTF is basically equals to 1 plus G of S into H of S equals to 0. This is what my characteristic equation is. Now like, from here what I can infer, what is my OLTF equals to? If this equation has to be satisfied, my G of S into H of S should be equals to -1. Okay, from here this is what I can infer, right? Okay, this is what I can infer. So like, for any value of S, whichever satisfies this equation, this will be my that value of S will be my closed loop pole. Okay, so this will be equals to at S equals to SP. Okay, so what is the point? For any complex or real, for any value of S, basically for any value of S complex / real, okay, that makes the OLTF equals to -1. That equals to -1, that will be called my closed loop pole, right? Okay, that will, okay, I wrote the OLTF. Actually my G of S, H of S also depends on K also. Okay, so what is my G of S, H of S? So let me write here, G of S, H of S is a function of, like, obviously function of S, okay, also K, right? System parameter K is at the top, right? K is at the top. So any value of S complex or real, and sorry, I have to mention here and also, okay, and also I have to mention, okay, and K, that makes my OLTF equals to -1. So for that like, for that condition, oh, okay, so I'm doing one thing wrong. Yeah, sorry, I meant something wrong. That like, I meant to say is that for any value of S that satisfies this one will be closed loop pole. It will be closed loop pole of the system, and that we get by that we get varying system parameter k. Okay, so we vary k and we get this value, right? Get this condition. We'll see, right? So let me prove it to you. So my g of s into h of s has to be equals to -1. So this is the basic condition. So here, right, I can deduce two conditions from here. One is my magnitude of g of s into h of s equals to 1 itself. And what is the another one? Another one is that angle of g of s into h of s equals to, what is the angle? Tell me, what is the angle of -1? What is the angle of 1? Angle of 1 is 0. So yeah, we'll also come to angles. So let me give you a brief overview. Where is 1 located? 1 is located around here, right? And we measure the angle with respect to this positive real axis. So with respect to positive real axis, what is the angle? 0 only, right? 0 only. Now what if my angle is located at, my point is located around -1? What is the angle with respect to this positive real axis? You can't say 0. So if you say 0, you are going from this direction. No, you have to go from this direction. So if you go from this direction, we have to rotate a full 180 degrees. So you can call it a plus minus 180 degrees, right? So yeah, generally we say it as 180, or you can say plus minus 180 same. You go clockwise or anti-clockwise, it doesn't matter, you're reaching the same point. So basically this angle of g of h of s will be plus minus 180 degrees. Okay, so this is what my angle of g of s into h of s is. Now this can be a odd multiple of plus minus 180 degrees. Why? Because if you put k equals to 1, k equals 0, what do you get? 180. If you put k equals to 1, what do you get? You get 180 times 3, which is 540, which is same only, because you are adding 360. So 360 is full rotation. Okay, so in angle terms, if you rotate a full circle, we come back to the same point only, so it doesn't matter. Okay, that's why we write it like this one, because this is generalized case and angles may sometimes come greater than 360. So for that case we do this. Okay, I will also explain angles a bit just in the next slide. So this is basically my k 0 1 and it is going on. So like what we do is like now obviously we'll come to questions. So what we do is, if in the question it has told us that some point s lies on the root locus and we have to find the value of k, for that case we use this location, this condition, basically this relation, this relation we use. What is the relation? Is we have to find like k is the unknown and s given, right? S is given. Okay, s is given and k is unknown. What is happening? Color blue. Yeah, k is the unknown and s is given. Now this is also known as the magnitude condition. Okay, because we are comparing the magnitude. So but this is only valid when we know exactly that my s lies on the root locus. If s doesn't lie on the root locus, then this won't be valid, right? Obviously this won't be valid. Okay, because what may also happen is that like when we solve, right, you can use to understand. Okay, I will just say this one, then I will say, let me first write a few things. So this is the, let me write in white, this is the magnitude condition. Okay, this is the magnitude condition basically. So now, right, and what is this called? This is called as the angle condition. So this is called as the angle condition. Okay, this is called as angle condition. Now right now what is this used for? This is used for when my s is not given and k is given. K is doesn't matter, k can be any parameter. Why? Because this is right independent of my k. How? Let me show you. So let me take one example, that g of s into h of s equals to, let's say it is k into s plus alpha into divided by s plus beta. So what is the angle? What is the angle? Angle basically, angle of g of s into h of s equals to basically tan inverse s plus b alpha, and it will be tan inverse s plus beta depending on the location. Okay, so depending on the location, so that I will come to. So as you can see, it is not depending at k at all. Angle does not depend on magnitude at all. So yeah, from here I can understand, okay, that this is independent of k. So this, like that angle in the bottom right, that will depend on the location of my poles. So that I will come to. Okay, so this, right, this is independent of k. So what is this used for? This is used for, okay, this condition, okay, this condition is used to check whether a test point lies in root locus or not. Okay, so this is the basic condition that I was telling, right? For any value of k, this can lie over here, right? This can lie over here, but obviously it has to satisfy this condition also. So like after satisfying this condition, I will find the value of k here. Okay, that's what I was, okay, my this one lagged. Just hold on a second, right? Yeah, sorry, actually, like that app crashed, and like the notes that I was writing, right, it also got deleted, so bit of it may change. Okay, I again rewrote few notes. Okay, this one, only this page, for this page, right? So we were here that I was writing, telling that what we should do was, like here, that same thing I was telling, right? So first I find whether that s test point lies in my root locus or not. Now after finding that one, what I do is come back to this condition and equate this condition and get my value of k, right? So both k and s are function, right? So yeah, I wrote it here that my open loop transfer function is both a function of s and k, both a function of s and k. So if these are both a function of s and k, then I will get it like this one. Okay, I will get it like this one. So I mean, first I will find, like, if they have already told us that this point lies in the root locus, then I will directly come to this condition and find the value of k, system parameter. Obviously they want me to find the value of k. Okay, but if they are asking, check whether this point lies in the root locus or not, you have to check, right? If you have to check, you can go with this parameter, okay, with the angle parameter. So because this is independent of k, you don't need the value of k. Okay, you just put the value of s over here and you check the angle. Now how to find angle? I have already explained angle, I think, in previous chapters also. I don't remember exactly, but again I will explain you once again. So these are my 4 coordinates. Okay, these are my 4 coordinates, and this is x and y. Okay, this is, let's say this is the complex plane, imaginary, x and jy, right? X and jy. Now what is happening? Now my theta is tan inverse y upon x. Okay, now what is theta equals to? So let's say this is one standard form where I have one location over here, that is x and j, x and y, x comma y. Okay, x comma y. So I have one standard location, x comma y. So this is one positive. So let's name this as, okay, let's name my x as 1 comma 1, right? 1 comma 1. Let's name x equals to y equals to 1. Okay, if my x and x comma y is 1 comma 1, what is this? So this point will be called 1 comma 1, and this is my theta, right? This is my theta. So this is basically what this theta represents. Okay, this is what this theta represents. Now what happens if my x and y are negative? So no, not negative, sorry, here, right, in this whole quadrant my x and y are positive, hence my angle is very simple to find. Okay, simple tan inverse y upon x. Now if my x is negative and my y is positive, so which quadrant I'm lying? I'm lying in the second quadrant. So let me take one vector here. Okay, again name this one as x is negative, right? So it will be -1 and y is positive, so it will be 1, and this is my theta. This is my theta, right? This is my theta. Okay, so now basically what will be the angle? Okay, sorry, this is not theta, sorry, okay, I have to, what will be the angle basically? So with respect to what I measure my angle, I told you, right, with respect to my positive x-axis. So I have to come all over here. Okay, I wrote the theta right, correct only, because how is it theta? Theta is what? Tan inverse y upon x. Basically what is tan theta? Tan theta is height upon base, right? So this is the height is 1 only, and base is again 1 only, right? But like magnitude of base is 1 only. So this is my angle of theta. Okay, this is my angle of theta. So what I can write over here, this is my theta. Okay, but I am not interested in this angle. What I am interested in is in this angle, right? In this angle. So what is the overall angle here? The overall angle is 180, right? Negative, right? It is going to negative, so it is going on half circle, it is 180, or you can say -180 also. Okay, but as I am going clockwise, I will say 180. Now 180 and some I have covered extra angular direction, right? So what I'll do, I'll subtract this extra angular direction. So in the second quadrant, my angle will be here, right? My angle will be 180 minus theta. 180 minus theta. Okay, so this will be my angle. Okay, or if you want to do clockwise, anti-clockwise, what you go? You will go -180, and then you will have to add, add another angle, right? So it will be -180 minus here. So that also you can do. Okay, -180 minus theta also you can do. How? Like just simply subtract 360 with this one. So subtracting 360 or adding 360 doesn't make any change to my angular location, because if you subtract 360, what does that mean? You simply rotate a full circle. You are in the same place. So like if you want to go from clockwise, this is -180 because clockwise is taken as negative. This is -180 and another theta I go. So another theta in the negative direction I go. So it is -180 minus theta. That you agree, right? That you agree. And what is this? This is 180 minus theta. So if I subtract this one with 360, what do I get? I get -180 minus theta. But what is the direction here? Direction here is clockwise. Direction here is anti-clockwise. Just be very careful with this angle thing. So always follow the anti-clockwise, you will be good to go. Okay, but if you want to go clockwise, you can write it like this one. Okay, so just be careful about the clockwise and anti-clockwise thing. I will just write the anti-clockwise thing from now, so that my students won't get confused. Okay, so now in this quadrant I got the angle. What is the angle in this quadrant? Now you tell me here, right? My x and y both are negative. If my x and y both are negative, what does that mean? So again, this is, let's say this is one, this is one. Okay, the lucky part is okay, what I will do is change the 1,1, because like you might say this one is also theta, right? Because this is also tan inverse 1 by 1. Okay, so I will change this one. Okay, else you will get confused. So I will write this one as 3,4. Like if both are 1,1 na, you will get confused. So this will be 3,4. Okay, and here also I will write not x equals to y equals to 1. I will write x equals to and this is, what is this? Now this is minus x, right? So this will be -3 and this will be 4. Okay, now can you tell me what will be the value of theta? Can you tell me? Here, right, it is tan inverse y upon x, which is 4/3. Here also tan inverse y upon x, which is 4/3. So this is theta. And what is this? This also I can measure, right? What is this? This is tan inverse y upon x, not y upon x. This is tan inverse x upon y. Why? Because this theta, right, is like measured with this opposite length and the base, right? Opposite length and the base. The opposite height goes in the top, okay, and the base goes in the denominator. So that I hope you understand, right? So not going into too much details of that one. So this is my theta. This is what I am interested in. So here tan inverse y upon x will be this one, right? 4 upon 3. Okay, and what is the angle? You tell me. It's 53.13. You have to remember this one in your head, right? So keep this in mind. So now here, right, my x and y both are negative in the third quadrant. So if my x and y both are negative, minus 3 minus 4, what is my theta? Again, right, my theta will be this one only. Why? Because my x is this one, okay, x is this one, and my y is this one, y is this one. So my theta should lie in the opposite of the y, right? Opposite of the y, like the theta and the y side should be facing each other, right? Opposite of them. So yeah, this is my y, so this is my theta, and this is not my theta. Okay, okay, you got it. So now, right, again this is my theta, so what will be my angle in the third quadrant? So my angle in the third quadrant will be, I'm rotating again full 180 degrees, okay, but now I have to rotate another extra theta in the anti-clockwise. So this will be plus theta, not minus theta, because I am rotating in anti-clockwise, not in clockwise. So this will be 180 plus theta, okay, for the third quadrant. This is for the, we'll write this one for the second quadrant. Okay, this is basically theta only, right? Theta only. Okay, I will write this in different color. Theta only for first quadrant. Okay, and this is basically for third quadrant, right? Third quadrant. And what is this equals? This is in the anti-clockwise, right? All of these are anti-clockwise. And what is this? This is fourth quadrant. Okay, so what is the angle for this one? So what I can say is, like, either you can rotate from here, but generally what the convention we do is, like, we say this is such a waste of time, so I have to rotate so much. This I will rotate clockwise direction, right? So here, right, what is my theta? So here, what is the x and y? X is positive, my y is negative. So if x is positive and my y is negative, okay, let me write this one as 3, 4, 3, 4. And what is my theta? So again, right, my angle will be opposite to my y side. So y is here, right? Y is here, so angle will be here. Okay, so my angle will be here, okay, as this is y. So what I can see is, obviously I can go all the way from here, but I'm just lazy, so I'll go in the clockwise direction this time. So if I go in the clockwise direction, what do I get? I get minus theta. So minus theta in the fourth quadrant. Minus theta in the clockwise direction, basically. Okay, I'm lazy. Okay, so yeah, I hope you got the points, like, which is and theta is what? Theta is this, right? Tan inverse y upon x. I'm not writing it, and it is tan inverse 4 upon 3. That is sorted, right? So yeah, these are the different angles in different coordinates. Why will this be useful? We'll see in the next few chapters. Basically, in this root locus also we'll see, and in further polar plot, Nyquist plot, all those chapters will use the concept of this finding the angle. Okay, I hope you understand that this is the first quadrant, and for the first quadrant, okay, my x and y both are positive. My x and y both are positive, then my angle is only theta, simple, tan inverse y upon x, no issues with that. Now if my x is negative and my y is positive, like this one, then my angle is 180 minus theta, right, in the anti-clockwise direction, and we will always use anti-clockwise only. Okay, and here if my angle is 180 plus theta, so this is basically this one, and okay, I can write this one like, take this anti-clockwise outside, and else you will get confused with theta only. Yeah, I have to put this one in bracket also. This one take outside, this one take outside. this one is this, okay, and this one is also anti-clockwise direction, okay. So yeah, so I will highlight these things. If we, okay, can I highlight this ones? Okay, if I highlight this one, this will go much. Let me highlight with this one. I will highlight this one, right? This is looking bad, and this is theta also. So yeah, like these are the angles of the 4 quadrants. I will understand for each condition when x is greater than less than 0. So I won't elaborate much. I will obviously, when solving questions there also, I'll understand, like explain you, right? So what is the another property? Another property is properties few, okay. Properties is basically that my minus 180 degrees equals to my 180 degree itself, because if I go from here to here or from here to here, both of them are same. And what is my another property? My theta plus any integer into 360, right, will be equals to theta itself. It doesn't matter, okay, it doesn't matter, okay. N can be an integer, any integer, negative, positive, it doesn't matter, because you are just rotating a full circle, okay. It doesn't matter, okay. How many number of circles you rotate, you come back to the same place again. Just like you rotate in your home, right? You rotate throughout the whole lawn and you come back to the same place, just like that. So yeah, these are few questions, okay. I will give you this one homeworks, and then in the next lecture we'll solve all this. This is the first question. So as I explained, right, the gain and magnitude parameter, sorry, the magnitude and the angle condition, okay. So those will be used here. I just gave you the hints, okay. And this one is the other question, basically. Sorry, like some call came up. Take a screenshot, okay. And these 2 questions will solve in the next lecture. Yeah, thank you for watching.